This is the second part of the alkanes chapter, and in this we will cover conformations, which is a very specific property of conformation is because of rotation around single bonds. Remember, all single bonds are sp3 hybridized, and in carbon, the single bonds are sp3 hybridized, which is only the alkanes family. Cycloalkanes also show conformation, but because rotation is not possible, they have a little bit different kind of isomers and conformation. And we'll talk about all of these when we get to the cyclic compounds. Right now, we'll focus more on the straight chain. One thing I want to mention before we go on is how to draw molecules out. So this projection that you see over here, this is called Fisher projection, which is also over here. And what it does is it takes two carbons and you look at how many hydrogens you have and where they are facing. So this is kind of how they are, and then you can rotate the hydrogens because the carbon is rotating. Now remember, this is a single bond. Remember, this is not like a rope or anything that is getting twisted. It's just a pair of electrons. So the twisting is not really twisting, okay, so much. It's just, it just goes on and on and on. So the sawhorse representation, which is also the Fisher representation, is not very clear. So we use what is called now the Newman projection, which is a little bit better. And in Newman projection, you draw a circle and then you draw three lines in the middle. Now this point right here is considered to be the front carbon, and the circle is supposed to be the back carbon. So it's almost as if you're looking directly at this carbon or at this carbon at eye level. So if you look at this one, then you don't really see two carbons. You see them right behind each other, and then all you will see on the side are hydrogen. So that's how we draw conformations for straight chain compounds. So this is called the Newman projection. So as we go on, we're going to learn about some different terminology regarding conformation. So the first one I want to talk about is the torsional strain. And the torsional strain arises when non-bonded atoms separated by three bonds, okay, one, two, and then third one there, are forced, okay, into a very specific location, and that usually happens because of sizes. It's not so much because of electronegativity or anything else. It's primarily because of the size. So which means that 1, 2, 3. Okay, these are the bonds that are affected. Remember, this is the front carbon. So 1, 2, the first bond here, second bond here, and the third bond here. So how are these three affected because of the size? So if the sizes are too big, then these atoms would like to move farther apart from each other because otherwise they'll be right behind each other. But if they're small, then they can stay in the way they can. So for example, this conformation is called the staggered conformation, which is also the most common one because in this case, they're all hydrogens anyway. So that's what this conformation is called, staggered. And then there is the eclipsed. In eclipsed, all the atoms are right behind each other. And this you can see is not going to be very stable because the two hydrogens are right behind each other. So it doesn't lend too much to the stability of the molecule. This molecule that we're looking at is ethane. Okay, so we only have two carbons and everything else is hydrogen. All right, still a little bit more. Dihedral angle, okay, and the dihedral angle is the angle that is between two of the closest atoms that you can see from one side, okay, and so it's not on the same carbon because remember on the same carbon the angle is always going to be 109 because it's sp3. So it's actually the atom that you have on the first carbon and the second one, okay, that are closest to each other. So what is the angle between them? That is called the dihedral angle. Then there is something called the steric strain. The steric strain is what we were talking about just now, where you have the big size atoms. Okay, so the atomic radii, that is what makes the atoms closer together or farther away. Really not closer, but more like farther away, because if they're too big, then they will want to be far away from each other. And then the angle strain is a little bit different thing. Angle strain is not so much for straight chain, it is a lot more for the cyclic compounds, and that arises when a bond is not in its appropriate angle. So for example, an sp3 is supposed to be 109 degrees, and if it's not 109 degrees, then it will have what we call angle strain. So these are the three keywords again for us to know. Here are the conformations of butane. Okay, now when you're looking at butane, here is the first structure, okay, to look at. Remember, this is the first carbon, this is the second carbon, and then you have two other carbons. All right, so it's made up of 4 carbons. In conformation analysis, you look at only 2 carbons at a time. You cannot look at more than 2 carbons at a time because the conformation is only for 2 carbons. For butane, there is no point looking at the first carbon and the second carbon because the first carbon has only hydrogens. And so hydrogens are not going to cause that much problem. But it's important to look at the second one because the first carbon is attached to a whole CH3 group, and then the second carbon, the third carbon is also attached to a CH3 group. Okay, so you can't look at the terminal carbons in this one. You can look only at the middle 2 carbons, carbons number 2 and 3. That is also an important exercise in conformation as to which 2 carbons you should be looking at. Anyhow, this is how we get started, okay, for conformation. And then what we do is we keep 1 carbon stable. So I usually keep my back carbon stable, which is this ring, okay, that is the back carbon, and you take the front one and you rotate it around. All right, so now what you're going to do is rotate it 60-degree angle. Okay, and that was the dihedral angle that we talked about. This is the dihedral angle. Okay, right here. This is 60 degrees. So we're going to rotate it 60 degrees. So if we do that 6 times, we will have 6 structures. Okay, because that's the complete one rotation. So here we go with the first rotation. Now remember, CH3 was down here. Now it's moved to here. Okay, so this is a nice structure where the CH3 and the CH3, the two methyl groups, are farthest away from each other. This is what we call anti. And so when the CH3 moves to the left 60 degrees, now this is an eclipse structure. Okay, but it's not totally eclipsed because the CH3 is behind or the H is behind CH3. They're behind each other, and so it's not so much of a steric hindrance, okay, or a steric strain. Then you rotate it once more, and if you do it one more rotation, then the energy comes down again because here it's relieved. Okay, now the CH3 is not in front of the hydrogen, so there is no more of that angle strain there, okay, or any kind of steric strain. Then you rotate it once more, okay, to the right, another 60 degrees, and look at that. The energy jumped up a lot. And this is a true eclipse structure, okay, because now you have a CH3 right behind another CH3, all right? And so these two CH3s have a 0 dihedral angle. And if it's a 0 dihedral angle, then it's going to be a highly stressed out molecule because you have two huge groups behind each other. Okay, so that is what we call the steric strain. So very high energy, and then again one other rotation comes down, okay, and then another rotation gives you eclipse, one more rotation, and this structure is the same as the first one, okay, the anti-anti. These two structures down here, these are known as gauche because the CH3s are next to each other, but not really behind each other or eclipsed with anything else. Sometimes gauche are also called staggered. And so we have anti, eclipse, gauche, eclipse. This is total eclipse, and then gauche, and then eclipse again, and then back to the anti. So these are the energy changes that go on as the bond is rotating. Looking at all of this, it's easy to see that this structure of butane, where the CH3 is right behind each other, is going to be the least stable structure. And here, the first one, the anti one, is going to be the most stable structure of all. Now, this may not seem so important in butane, but this becomes really important when you have larger molecules because then they are stuck in their conformation, and then you cannot get them to do certain things for you. So either they will not attach to enzyme locations, or they will not do certain reactions because they are stuck, okay, in whatever shape they are or whatever angle they are because of this kind of strains, okay, that they have. So here are some examples, and these are not exactly solved examples because I've not drawn out the structures for you. This is an exercise for you to do, but I'm going to give you hints on how you can start doing this. So here are 4 different kinds of alcohols possible with 4 carbons, okay, which means you have an OH group in there because it's an alcohol. Don't worry about the nomenclature so much because we haven't quite done it yet, but the names are given just in case you want to kind of start getting familiar with the name. So this is 1-butanol. This is 2-butanol because the alcohol has moved to the 2. This is isobutyl alcohol because this functional group, this alkyl group right here is the isobutyl. And here this alkyl group is T-butyl. And so this is 2-butyl alcohol. So anyhow, these are the 4 constitutional isomers for alcohol. And the question is, draw as many compounds as you can with that, and then draw their conformation conformers as well. So what you will have to do in these cases, okay, is if you draw all of this out, then you have to kind of see, all right, which 2 carbons am I going to look at? Am I going to look at these 2, these 2, these 2? And which of these molecules is going to have the highest strain? Okay, now not all your questions are going to be like that. Usually I just give you 1 compound, and for that one you have to draw the 6 structures out. Okay, but in this one I'm taking this a little step further so you can see how different compounds can have different kind of conformers. So this compound here, no branching whatsoever, just have hydrogens all the way. Here you have a little branching going on because now the OH has moved from the end carbon to the second carbon. And here, of course, there is some serious branching going on because in these 2 carbons, you have 1 methyl group and then an OH group. And then here, it may seem bulky, but it really is not, okay? Because on the same carbon, you have 3 bulky groups, okay? But on the next carbon, you have 3 hydrogens. So this compound, actually, the T-butyl alcohol, will be the most stable. Anyhow, you cannot draw too many conformers for this one because these are the 2 carbons that you will be looking at, or these 2, and they are the same, and hydrogen really does not have that much of um, steric hindrance. All right, and so this structure is probably not very good one to study. We can look at this structure over here. You can draw conformers for these 2 carbons. Again, try not to take the terminal carbon unless you have any group on it, because in this case, if you have 3 hydrogens, it's not worth it. Okay, so you move on to the next carbon. You look at these 2 carbons. Now on this carbon, you have 2 hydrogens attached and a CH3. On this carbon, you'll have 2 hydrogens attached and this whole CH2OH group. Okay, so just focus on these 2 and then you draw your 6 structures out. Okay, the same thing happens when you look at this carbon and this one, which is this is carbon number 1, carbon number 2. So if you look at 1 and 2, then also you can draw conformers because carbon number 1 is going to have 2 hydrogens and an alcohol group, and carbon number 2 is going to have 2 hydrogens and an ethyl group. So the ethyl group and the OH group, the alcohol group, they both can have the eclipsed and the anti-conformers. Okay, so this will definitely lend to some very good structures for you to study. This one over here, the only 2 carbons that you can study are carbon number 2 and 3. The first and the last one over here, they're both CH3, so no point looking at them. You can only study these 2 carbons because in the carbon number 1, you have alcohol, hydrogen, and a methyl group. And in case of the third carbon, you have 2 hydrogens and a methyl group. So yes, this will also give you some very interesting structures. And then in this case, you have this methyl group and you have that methyl group. So again, don't look at these 2 carbons, don't look at these 2 carbons. Focus on these 2 carbons and then you can draw some nice structures out. So all of these examples, the first 3, they will have good structures. So practice that out. I will try and do them and supplement that as the pencast, okay? This one will not have any conformers. This one is not very interesting molecule as far as that is concerned. Now let's look at some cycloalkanes. As far as the alkanes are concerned, that's the only thing that can happen is the is the rotation around the single bond. Now with the cycloalkanes, things are a little bit different, okay? Because in cycloalkanes, you have two things that are going to be different, okay? One is angle strain, and the other thing is that they are cyclic compounds, so they don't rotate. So the angle strain occurs because the bonds can be different from 109. All alkanes are sp3 hybridized, so technically their bonds should be 109. So if it is anything different than 109, then it's not going to be very stable, and that is the angle strain. Torsional strain, again, this is caused by the eclipsing of the CH bonds. Steric strain, again, the same thing, caused by proximity of large atoms or groups, okay? Or it could be small atoms too, but usually it's the large atoms or the large groups. Cycloalkanes are less flexible because, yeah, they're cyclic. Okay, you can't rotate them or anything like that. But because of their cyclic structure, they have a top face and a bottom face. Okay, and that's an important thing because now, because of that, you start having isomers. All right, and so isomers occur where you have the same molecular formula but different structures. Okay, and in this case, we're going to call them cis and trans isomers, which are also called geometric isomers. And in case of geometric isomers, you have cis and trans isomerism. Cis and trans isomerism is when the two hydrogens are on the same side, that is called cis. When the hydrogens are on the opposite sides, they're called trans. Remember, the cis and trans has to do with the hydrogens, not with the other groups. So these CH3 groups, they could be anything. They could be chlorine, they could be bromine or ethyl group, whatever it is. But if you don't have these two hydrogens, then you cannot call it cis or trans. Okay, so the cis and trans has to do with hydrogens being on the same side or being on the opposite side. Okay, and this is called geometric isomerism. So let's talk about cyclopropane, which is the smallest ring possible. And cyclopropane is pretty stressed out ring, okay, because the ring is 3 carbons, and in a triangle, the bond angle is very, very small. Okay, it's 60 degrees inside, and it's very large for the hydrogens outside. So because of the 60-degree angle strain over here, this ring is highly stressed out, and you really don't find it too much. Okay, it's very hard to make, and it's also very hard to keep. Okay, so these kind of compounds will be a little bit more reactive. Cyclobutane is getting a little bit different because now in this case you have a square structure, and in the square structure you have a bond angle of 90 degrees, and in case of 90-degree angle, it's also stressed out because it's still not 109. Okay, it's still about 20 degrees away from what it's meant to be. So this is also a very stressful molecule. Cyclobutanes make for very good explosives, okay, because they are highly stressed out. Continuing on to cyclopentane. Cyclopentane is now getting a little bit better. The bond angle is now 108, the internal one, and excuse me, the dihedral angle is 108, and the inner angle is about 120. And so it's really quite stable, and it's what we call puckered, okay, which means it's a little bit out of plane. The first two rings, cyclopropane and cyclobutane, they were planar rings, which means they're completely flat, but cyclopentane is slightly bent, okay, and that's called puckered, but you can call it bent too, okay, that's fine. So it's little slightly angular ring, and so it kind of lends to the stability, okay, of the ring also. So 5-membered rings are actually quite common. And then cyclohexane ring is one of the most stable ring. Okay, the inner angle is 120, and this is what it looks like. It is completely out of plane now. Okay, and so this is a very stable ring. Cyclohexanes are found in the nature all the time. Okay, cyclopentanes and cyclohexanes, very, very common. As far as the conformations are concerned, we are going to look more at cyclohexane. Cyclopentane does not have that many conformers because all this carbon can do here is it can flip up or you can flip it down. Up, down. That's all it can do. On the other hand, with the cyclohexane ring, you have two carbons that can flip up and down, okay? So this can go up and this can go down, all right? And so when you have two carbons that can go up and down, it changes how these atoms will start behaving, okay, or how they'll be affected by each other. So cyclohexane is the cycloalkane that we will study in conformation. So here is the conformation of cyclohexane. This one, as I will show in class also, and there is a video that you need to see for this one. Okay, it's coming up in the next slides. And what happens is that because you really cannot break any bond for rotation, the only thing that the ring can do is what we call a ring flip. Okay, which means that one carbon atom can move up, the other one can then move down. Okay, that's about it. You can't twist the ring because then it's not very stable right here. This is the twist boat. Okay, so where the ring is trying to get a little twisted, not very good idea. And then here's the boat conformation, in which case you can see that this atom has moved up. So once it moves up, it kind of looks like a boat. Okay, so that's called the boat conformation. Going from boat to this other conformation, which is called the chair conformation, it has to go through the twist boat, and then it comes down to the chair conformation. Okay, and the chair conformation, in case you can't see, it's like a lazy boy chair. Okay, so here is the back, here is the seat, and here is the leg rest. Okay, so remember, this is how the ring is going right now. In this case, the lazy boy is completely opposite. Okay, here is the back, here is the seat, and here is the leg rest. Okay, completely opposite. And that's what's happened. Okay, flip. When we talk about conformers for cyclohexane, these are the two chair conformations we talk about because these two are the stable ones. We do not talk about the boat or the twist. So if I ask you to draw me conformers of cyclohexane, please limit it to the chair conformation only. Drawing the cyclohexane is also an interesting thing because you have to draw it correctly. If you do not draw it correctly, then I will not give you points. It's as simple as that. So please learn how to draw this. It's quite simple. You start with two parallel lines, and then whatever lines are coming down or whatever two carbons are going down, so you draw a carbon up on the top and join it, and then whatever carbons are going up, you draw a carbon on down and join it down here. That's it. If your lines were going up this way, the other way, if they're going up this way, then your carbon will be down here and up there. Okay, so make sure you learn this properly. There are two different kinds of hydrogens on any kind of a cycloalkane. So the two, one of is called axial, the other one is called equatorial. The axial hydrogens are going completely up or completely down, like the axis on the earth. Okay, completely going up, completely going down. These are drawn in pink over here. The second ones are called equatorial hydrogens, and equatorial hydrogens are like the equator. All right, and these are the blue ones, okay, that we have. And the blue ones are going at an angle, okay, and this is again like an equator, so it's going horizontal. The axial hydrogens, remember, up and down, all right, whereas the equatorials are going a little bit more horizontal, but they're still angular. Okay, they're not completely straight. Okay, all right. The other thing that you need to note about the axial bonds and the equatorial hydrogens is that the axial hydrogens bonds, whatever, if one is going up, the other one is going down. The next one up, the next one down. So it's always one up, one down, one up, one down. That's how it is. The same thing goes for equatorial bonds. Sometimes it's a little bit hard to see, but again, if you see these two carbons right at your eye level, you will see it. Okay, and that's when you will see that these bonds are not exactly horizontal. So this bond is going down. This equatorial is going up, down, up, down, up. Okay, again, alternate. The other thing about the axial and equatorial is that if the axial is going up, the equatorial is going down. Axial is going down, equatorial is going up. All right, and that relationship never loses even when you do a ring flip. Okay, So that's an important thing. You have to learn how to draw these also. Do not draw the axials at an angle because the axials go straight up and straight down. You have to draw the equatorials at an angle. So we'll go over this in class also. The ring flip. This is the most interesting part of the conformation because after all, this is the conformation, okay, for cyclohexane. I would really like you to go to these two links over here and see how the ring flip works. There's some nice animation, and then there's a professor showing the ring flip also. I will show this to you in class, but you can go over here in case you're studying this on your own. Okay, and so a ring flip is when you move one carbon up and the other one down. Okay, so this carbon is this carbon. All right, so this was down, this has gone up. All right, this was up, this has gone down. All right, so it's a ring flip right here. Okay, this is how it would look in a stick model. This is a ball and stick model. This is just a stick model. So this carbon has gone up and that carbon has come down. Okay, now remember what I told you about the axials and the equatorials. All right, what happens during a ring flip is that all the axials become equatorials. So look at the pink ones over here, okay? All the axials become equatorials. All the equatorials become axial. That's the magic of ring flip. And this is why we have ring flips in cyclohexane, because some of those axials may show steric hindrance, all right? And some of those equatorials may provide some relief. So we'll have to go over this one in a minute, but anyhow, this is what the ring flip is about, okay? The other thing I want you to note is that this axial was going up. This axial, which became equatorial, is still going up. It is not going down, all right? So this is going up. This is going up. This equatorial was going down, and so it became down for axial also. All right, that is how things work for conformers for cyclohexane. Here are some structures that you may want to practice. There are different kinds, so they are all cyclohexane first of all. But what is different about them is that they are di-substituted, so you have two methyl groups. So you do two isomers, okay, of the 1,2 relationship. 1,2 relationship can be cis or it can be trans. So then you have the 1,3 isomers, okay, or the 1,3 relationship, and then the 1,3 you have again cis and trans, and then the last relationship is the 1,4 relationship where you have cis and then trans. Okay, again, remember the trans has to do with the hydrogens, all right, and this is also has to do with the hydrogens. So when you have cis, okay, relationship, the cis relationship means that the two hydrogens are going in the same direction. When the two hydrogens are going in the same direction, it means they're either both going down or they're both going up. This is a very important thing to remember. I will tell you what it is not. Okay, so if you don't want to listen to it, you don't have to listen to this now. The cis and trans have nothing to do with two hydrogens being equatorial or axial. It has to do with whether they are going up or down. Okay, so here, now you can start listening. The cis and the trans, that has to do with the relationship between these two hydrogens. So in case of cis, the two hydrogens are going up. In the trans relationship, one hydrogen is going up, one is going down. Okay, so that's how you have to draw it. Which means in case of cis, if they're both going up, one has to be axial, the other one has to be equatorial, because remember the alternate bonds. Okay, so if axial is going up, the equatorial has to be going up. So in case there is trans, which means one is going up, one is going down, then axial is going up, equatorial is going, or the other axial is going down. Okay, so that's what happens. So in this case, in case of trans, the two hydrogens will be axial or equatorial. In case of cis, they will be axial and equatorial. Okay, that's how it will be. Those are the relationships that you have for these two. But the best thing to do is draw the models for this one and then see how the ring flip works, or you can just draw the ring flip in your notebook, okay, and practice all of this. This is a really nice exercise, okay, to work on. This is one example of the ring flip. So go through this one carefully. If you take this carbon and you do a ring flip and you bring it down, this axial CH3, which was going up, is now equatorial. It's going up. Okay. This was a trans relationship, so CH3 is going up, CH3 is going down, or the hydrogen equatorial is going down and hydrogen equatorial is going up. Okay, so in this case, we're looking at the CH3 because the CH3 is the bulky group. Hydrogen is not bulky, so it doesn't matter, all right? But the CH3 group is the bulky group. So the location of the CH3 is what matters, all right? So in this case, the CH3 is axial. This CH3 is also axial. And so what happens is that because of this, there is some sort of a steric hindrance. Okay, so you have hydrogens coming out here, and then you have hydrogens going down, which are the axial ones. And so they give for a little bit of an angle, steric hindrance. In this case, when the CH3s, the methyl groups, are equatorial and they're going outside, then they're actually quite free. All right, so there is no more steric hindrance. And so it turns out that this conformer is more stable than this one. And this really is your exercise in or your questions that you would get for conformers, is that which conformer is more stable. So you look for the bulky groups. If the bulky groups is axial, it's not going to be stable. If the bulky group is equatorial, it's going to be stable. Whether the equatorial group is going up or down, it doesn't matter. Okay, so long it's equatorial, it's going to be stable. All right, and here we have the cis. In the cis, you can see it doesn't really matter because one group is axial going up, the other one is equatorial going up. And so when you do the ring flip, it's the same thing. You still have one equatorial going up and the other axial going up. All right, so which means that it really doesn't have any effect, which means these two structures are equal in energy. All right, and they don't really affect the stability of the structure, but trans definitely does. Okay, and so you really just have to do this to figure it out. Okay, you can't look at a structure and predict unless you memorize everything, which I don't want you to. Lastly, here are your concepts. You need to know what conformation is. Anti-gauche, eclipse. Remember, these are the three key conformers for straight chain alkanes. Then we have the different kind of strains possible: torsional, angle, and steric. Torsional is when you have the two groups. Okay, what kind of groups you have behind each other. Angle strain is when the angle is too small, which usually it's not then, because it will relieve itself, okay, by moving. And then steric hindrance is because of the bulky group. When you start having cycloalkanes, then you will have cis and trans isomers, you'll have chair conformers, and you have equatorial and axial substituents. Okay, remember I wrote only chair conformation. I did not write the other ones because those ones are not stable at all, so we don't even study them. The most important thing for this chapter is for you to practice the structures. If you don't draw them out, you will never get it. Okay, so make sure you take the time and draw the structures.